Introduction: Pipelining. Pipelining is a powerful implementation technique for enhancing system throughput without requiring massive replication of hardware. Most of the techniques that constituted the RISC approach are directly or indirectly related to the objective of efficient pipelining. Pipelining has been effectively applied to CISC processors as well. The Intel i486 was the first pipeline implementation of the IA32 architecture. Pipeline versions of Digital's VAX and Motorola's M68K architectures were quite successful. Pipelining is a technique that is now widely employed in the design of instruction set processors. Many of the approaches and techniques related to the design of pipeline processors are fundamental to the design of superscalar processors, such as pipeline interlock mechanisms for hazard detection and resolution. The current trend is toward very deep pipelines. Pipeline depth has increased from less than 10 to more than 20. Deep pipelines are necessary for achieving very high clock frequencies. This has been a very effective means of gaining greater processor performance. This trend will continue. Types of pipelining: linear pipelines, non-linear pipelines, single-function pipelines, multifunctional pipelines, static and dynamic. Principles of linear pipelining. Basic principles and structure. Let T be a task which can be partitioned into K. Subtasks according to the linear precedence relation. T equals T1, T2, and so on until Tk. That is, a subtraction not start until are finished. This can be modeled with the linear precedence graph. Linear pipeline, no feedback, can always be constructed to process a succession of subtasks with a linear precedence graph. Basic structure and control of a linear pipeline processor. L stands for latch, C for clock, Si, the ith stage. Linear pipeline processor. Linear pipeline processes a sequence of subtasks with linear precedence. At a higher level, sequence of processors. Data flowing in streams from stage S1 to the final stage Sk. Control of data flow, synchronous or asynchronous. Learning objectives. In this chapter, the user would learn the following in detail: asynchronous data transfer, handshaking, asynchronous serial transfer, interrupt initiated input-output, Dma transfer, interfacing peripherals with CPU, introduction, keyboard, mouse, printer, scanner, network card. Introduction to pipelining and linear pipelining processor. Input-output interface. Input-output interface provides a method for transferring information between internal storage and external input-output devices. Each computer system has a special hardware component between CPU and the peripherals, which supervises and synchronizes all input and output transfers. These components are called interface units. Input-output bus and interface modules. The input-output bus consists of data lines, address lines, and control lines. The device along with its interface is connected to these buses. Each interface has address decoder, which decodes the address which is received from the input-output bus and gives control to the appropriate devices. Each interface also has controller, which supervises and synchronizes data transfer between peripheral devices and the processor. Input-output command. When the address is made available in the address line, the processor provides a function code in the control lines. Therefore, the selected device responds to the function code and executes the operation. This is known as input-output command. There are three types of input-output function codes that an interface may receive: control command, status command, or data output command. Control command. This command is issued to activate the peripheral and to inform it what to do. For example, using tapes we can perform the following operations: rewind the tape, move in forward direction, erasing the information, etc. Status command. It is used to test various status conditions in the interface and the peripheral. For example, the computer may wish to check the status of peripheral before the transfer is initiated. Data output command. It causes the interface to respond by transferring data from the bus into one of its registers. Example, the processor monitors the operation of tape when it is in the correct position. It issues data output command so the information from the data line is transferred to the buffer register of a device. The interface receives data from the peripheral and places it into the memory. Input-output versus memory bus. Two separate buses, one for memory and the other for input-output. One common bus for both memory and input-output, but separate control line for each input-output, read, input-output, write, memory read and memory write. Uses one common bus for both memory and input-output with common control line. In the first method, two separate buses, the computer has independent set of address, data and control bus for both input-output and memory. For performing operations simultaneously with input-output and memory, two processors are available. CPU will perform memory-related operation. IOP will perform IO-related operation. IOP is otherwise called as data channel. Most computers use one common bus for performing operations with IO and memory, whereas separate control buses are available for these two operations. This control signal identifies which device is using currently based on the following information: input-output read, input-output write, memory read, memory write. The CPU specifies whether the address on the address line is meant for IO device or memory. The control signal specifies which device is to be chosen for operation. This technique is otherwise called isolated IO because the device is isolated. The control signal chooses the appropriate device. This technique uses same address space for both memory and input-output. Therefore, we can perform either memory-related instruction or IO-related instruction separately. This configuration is also called memory-mapped IO. The CPU manipulates all instruction whether it is an IO-related instruction or it is a memory-related instruction. Example for IO interface. In the above diagram, it consists of two data registers called port A, port B, control and status register, bus buffer and timing and control unit. The peripheral communicates to CPU through the internal bus. Chip select and register unit will select the appropriate register during operation. When CS is active and RS1, RS0 is 01 port B, register 1 is selected for read-write operation. RS1, RS0 is 10. Control registers are active by checking and supervising the device performance. When RS1, RS0 is 11, status register is active, which informs the CPU the status of a particular register. The bits in status register are used for checking special status condition like the status of the device. Asynchronous data transfer, handshaking signal method. Two independent units which require control signal can be transmitted by the communication units to indicate the time at which data is transferred. Synchronous and asynchronous operations. Synchronous data transfer. All devices derive the timing information from common clock line. Asynchronous data transfer. No common clock. two asynchronous data transfer methods: strobe signal method and handshaking method. Strobe signal method. The strobe pulse is supplied by one of the units to indicate the other unit when data transfer occurs. There are two methods of data transfer: source-initiated data transfer and destination-initiated data transfer. Source-initiated data transfer. It is an asynchronous data transfer and it employs single control line to time each transfer. Source unit enables the destination unit by sending strobe signal. After a few seconds, data is placed in data bus. When destination is alerted by accepting the strobe signal first and it is ready to accept data. The timing diagram shows at the rising edge of strobe signal, valid data is placed in the data bus and it is transmitted to the destination. Destination-initiated data transfer. The destination-initiated transfer requires strobe signal transferred by the destination unit when it is active. The source unit responds by placing data in the data bus and transmits to the destination unit. The strobe signal is controlled by the CPU depending upon the operation, which is initiated by either source unit or destination unit. The timing diagram shows the relationship between the source unit and destination unit in the rising edge of clock pulse. When the edge falls, the transfer is completed and each unit is deactivated. Disadvantage. The source unit which initiates the transfer does not know whether the destination has received the data item that was placed in the bus. Similarly, the destination-initiated transfer does not know whether destination has accepted the data. Handshaking signal method. Each data item is transmitted with a control signal that indicates the presence of data in the bus. The receiving unit responds with another control signal to acknowledge the receipt of data. This control signal is called a handshaking signal. There are two methods of data transfer: source-initiated data transfer and destination-initiated data transfer. For example, we consider the transmitting unit as the source unit and the receiving unit as the destination unit. That is, CPU is the source unit during output or writes operation. It is the destination unit during input or read operation. Two-wire control. The handshaking method solves the problem of data acknowledgement in the above diagram. The data transfer procedure is initiated by the source. It generates two signals called data valid and places data on the data bus. Destination unit generates data accepted signal. The timing diagram shows the exchange of signal between the two units. The diagram C part shows source unit places data on the data bus and enables data valid signal. Destination unit accepted the data and enables data accepted line. Source unit waits for the data accepted signal and disables data valid and data on the data bus line. When source accepts the data accepted line, it enables the data valid and data on the data bus line. At the same time, destination disables data accepted line. Handshaking, destination-initiated transfer. In destination-initiated transfer, destination unit generates a special signal called ready for data to intimate to the source unit that it is ready to accept data. Until this signal is accepted by the source unit, it won't place data on the data bus and also it won't enable data valid line. Source unit places data on the data bus and enables data valid line when it receives ready for data signal. Destination unit waits for data and it disables ready for data line. When destination accepts the data, it enables ready for line signal. At the same time, source unit disables data valid line and invalidates data on the data bus. Timeout mechanism. The handshaking scheme provides a high degree of flexibility and reliability because the successful completion of data transfer relies on active participant on both sides. If one unit is faulty or slow, the data transfer will not complete in time. Such error is to be detected by the timeout mechanism, which produces an alarm to any one unit when the data transfer is not completed in a predetermined time. The timeout is implemented by means of an internal clock that starts counting time when the unit enables one of its any inform control signals. The timeout signal can be used to interrupt the processor and execute a service routine that takes error recovery action. Asynchronous serial transfer. The transfer of data between two units may be serial or parallel. Parallel transfer. In a parallel data transmission, each bit of the message has its own path and the total message has been transmitted at the same time. Serial transfer. In this technique, each bit in the message is sent in the sequence one at a time. In asynchronous serial transfer, each character consists of three parts. UART, Universal Asynchronous Receiver Transmitter. ICs are available. It is specially designed to provide the interface between the computer and similar interactive terminals. Such circuits are called UART or Asynchronous Communication Interface. Every key is pressed through input device. Each key's 8-bit information is transmitted to 11-bit format, processed by the CPU in the same 8-bit format. When it delivers the output, the 11-bit format is again converted to 8-bit format. This conversion is done by the UART. Asynchronous Communication Interface. The interface is initialized for a particular mode of transfer by means of control byte from the CPU to control register. When transmitter register accepts data from the CPU, that is, the output function shift register takes each character one at a time from the transmitted register and it is given to the peripheral in the form of output. When the system accepts input, CPU chooses the appropriate receiver register which gets input one at a time from the shift register and it is transmitted to the memory. These two operations are performed by using chip select and register select input, which chooses the appropriate register for a particular operation. Asynchronous Communication Interface. Transmitter. The operation of transmitter portion of the interface is as follows. CPU reads the status register and checks the flag to see if the transmitter register is empty or not. If it is empty, the data are transmitted from the CPU through bidirectional data buffer and it is loaded in the transmitter register. The character is transferred in parallel from transmitter register to the shift register and the appropriate number of stop bits is added. When shift register accepts each character, it encounters stop bit. It informs to the CPU that transmitter register is empty again. Therefore, the CPU transfers another set of characters by checking the status flag of register. Double buffered. The interface is said to be double buffered because a new character is loaded in the transmitter register as soon as the previous character is transmitted to the shift register. Receiver. The operation of receiver is similar to the transmitter. The received data input is 1. That is, the line is idle. The receiver interface monitors for 0 signal, that is, the start bit of a character. Once it is detected, the incoming bits or the valid data, that is, shifted from shift register to receiver register at the prescribed baud rate. Fifo Buffer. Fifo Buffer is a memory unit that stores information in such a manner that an item first inserted is to be removed first. It consists of separate input-output terminal and each operates in different mode. The following diagram shows 4x4 Fifo buffer. Each buffer consists of a register and each register consists of 4 bits. A controlled register with flip-flop Fi, I equals 1, 2, 3 or 4 is used 1 for each register. The flip-flop Fi is set to 1. which indicates that a 4-bit data is stored in the corresponding register. A 0 in Fi indicates that the corresponding register does not contain valid data. The data in the register moves down the Fifo buffer towards an output end as long as there are empty locations in the register. Data are inserted into the buffer when the input-ready signal is enabled. This occurs when the first flip-flop F1 is 0, indicating that R1 is empty, which enables the clock in R1 through the insert control line. In the same clock which set F1 to 1, it indicates that input-ready signal is disabled. That is, data are loaded into the first buffer and which enables to accept data currently. This process is repeated 4 times so that the information is shifted from left-hand register to right-hand register one at a time. When all the 4 registers are full, output-ready control line is enabled, which is set at F4 equals 1, indicating that valid data are available in R4 register. This data is accepted by the destination unit by enabling delete signal, which causes data from the 4th register to be sent as an output. In this fashion, input is inserted from the left-hand side and it is deleted from the right-hand side. Interrupt-initiated input-output. Modes of data transfer. Binary information transferred from central computer to an external device originates in the memory unit. Data transfer to and from peripheral can be handled in 4 ways. Programmed input-output, interrupt-initiated input-output, DMA, input-output processor, IOP. Programmed input-output. This operation is the result of input-output instruction written in assembly language program. Each data that is going to be transferred is initiated by the instruction in the program. The above diagram shows an example of programmed input-output where data transfer occurs through input-output device that passes through interface and is stored in CPU register. The device transfers bytes of data and it is placed in input-output bus and enables data valid line. The interface accepts the data valid line and clears data register to store valid data. That is available in the I/O bus. It sends data accepted line to the device. At the same time, interface sets status register flag bit to 1. That time the device disables data valid line. CPU checks the flag bit in the status register. If flag bit is 1, data is available in data register, therefore it reads data. After reading data from the data register, flag bit is cleared to 0. It indicates that data register is empty. Therefore, input-output device transfers another data. The flowchart illustrates the operation of CPU. Therefore, for each transfer, it requires 3 instructions. Interrupt-initiated input-output. In the programmed input-output method, CPU has to check whether data is placed in the data register or not. This is a time-consuming activity. To avoid this, interrupt-initiated input-output technique is used. When data is placed in the data register, the interface gives interrupt to the CPU that data is available in the data register. Therefore, CPU reads the data. Meanwhile, CPU temporarily stops executing current instruction and it transfers data from the data register. There are 2 types of interrupt in the hardware consideration: vectored interrupt and non-vectored interrupt. Hardware consideration. Vectored interrupt. In this method, the source unit that interrupts the CPU supplies the branch information. Non-vectored interrupt. In this method, the branch address is assigned to a fixed location in memory Therefore, every time interrupt occurs, CPU goes to fixed location. Software consideration. A program instruction must specify the branch information. Therefore, the input-output routine must issue control commands to activate the peripheral when the data is ready. Priority interrupt. A priority interrupt is a system that establishes a priority over various devices to determine which device is to be serviced first when two or more requests arrive simultaneously. The priority is assigned by either the hardware or software routine. For example, magnetic disk is having higher priority and keyboard is having lower priority. Polling technique. The polling technique is used to assign priority for multiple devices by the software routine. Daisy chaining priority. This technique establishes serial connection of devices that request an interrupt. The device with the highest priority is placed first. The lowest priority will be placed in the next level. The interrupt request line is common to the entire device. When this line goes low, it enables interrupt input to the CPU. When no interrupt is pending, this line goes high. Priority logic. The following diagram consists of two register interrupt registers whose bit position is set or clear depending upon the request given by particular device. The highest priority device occupies first position than lower priority device which occupies lowest position. The mask register, which is having the same bit position line interrupt register, which is set or cleared by the program instruction, which indicates the priority of the device to be enabled. Using AND gauge priority encoder accept input, it fetches the corresponding vector address to the CPU to go through interrupt service routine. Another output from the encoder set interrupt status register. Accordingly, interrupts enabled register is also set. Therefore, interrupt request will be given to the CPU. When CPU gives acknowledgement, it enables the vector address. Corresponding device location fetches the address and it goes to interrupt service routine. Interrupt cycle. At the end of each instruction cycle, CPU checks IEN and IST. If both IEN and IST is equal to 1, CPU goes to an instruction cycle. Sequence of micro operation during instruction cycle. Decrement stack pointers. Push the PC into stack. Enable intact. Interrupt acknowledge. Transfer VAD, vector address, to program counter PC. Software routine. The computer must also have software routine for servicing interrupt request and control interrupt hardware register. In the following diagram, each device has its corresponding service routine. When that device is active, the corresponding service routine will be executed and user performs reading and writing operation with that device. Initial and final operation. Each interrupt service routine must have both initial and final set of operations for controlling the register in the hardware system. The initiated operations are: low-level mask register will be cleared, clear IST, save the content of processor register, set IEN, proceed with service routine. The final operation includes the following things: clear IEN, restore the content of processor register, clear the bit in the interrupt register belonging to the source that has been serviced. Set lower priority bit in the mask register will be enabled. Restore return address into PC and set enable the interrupt register. An initial and final operation is called as overhead operations or housekeeping chores. DMA controller, interface which allows input-output transfer directly between memory and device, freeing CPU for other tasks. CPU initializes DMA controller by sending memory address and the block size, the number of words. The bus request control line is used by the DMA controller to request the bus from the CPU to transfer data directly into the memory. When CPU is performing any operation, it stops temporarily and releases those buses and enables bus grant control line. When bus grant control signal is active, input-output devices uses all the buses to transfer data directly from memory at the same time. Direct memory access. DMA controller takes over the buses to manage the transfer directly between the input-output device and memory. Block of data transfer from high-speed devices, drum, disk, and tape. DMA controller. The DMA controller needs the usual circuit of an interface to communicate with the CPU and input-output device. In addition, device address register, word count register, control register are available to transfer data directly to the memory. DMA initialization process. Set address register, memory address for read and write. Set word count register, the number of words to transfer. Set transfer mode, read write, burst or cycle stealing. Input output to input output, input output to memory, memory to memory, memory search, input output search. DMA transfer start, EOT, end of transfer. DMA controller control logic. The unit communicates with the CPU through data bus and control lines. The register in the DMA is chosen by the CPU through address bus by enabling DMA select and register select control line. After choosing the corresponding register, reading or writing is performed. When BG equals 0, CPU communicates directly with all DMA registers. When BG equals 1, CPU releases all the buses so that the input-output device is directly connected to memory using that bus and communication is established. When BG equals 1, CPU initializes DMA by sending the following information: the starting address of memory where data is available, word count, number of words present in the memory block, control to specify read or write operation. DMA transfer. The CPU communicates with the DMA controller through address and data buses, and also DMA is having their own address and data bus. When input-output device requesting for DMA transfer, DMA controller accepts this request and asks the CPU for releasing buses by enabling bus request line. When CPU accepts this input, it blocks all the buses and allocates to the DMA controller by enabling bus grant signal. The DMA controller accepts this signal and sends DMA acknowledgement to the input-output device. Therefore, input-output device directly accesses memory with the help of DMA controller buses to transfer data directly from memory. The address select logic will select the appropriate register in the DMA by making use of DS and RS signal. Interfacing peripherals with CPU. The input-output subsystem of a computer, referred to as I/O, provides an efficient mode of communication between the computer and the outside environment. Input or output devices attached to the computer through I/O ports are called peripherals. The most common peripherals are keyboards, display units and printers, modem and network cards. Transmission mode. The term transmission mode refers to the direction of information flow between two devices. There are three types of transmission modes: Simplex, Half-Duplex, and Full-Duplex. Simplex transmission. In Simplex mode, the communication mode is unidirectional, which means only one of the two stations or devices on a link can transmit, the other can only receive. Keyboards and traditional monitors are both examples of Simplex devices. The keyboard can only introduce input. The monitor can only accept input. Half-duplex transmission. In half-duplex mode, both the stations can transmit and receive, but not at the same time. When one device is sending, the other can only receive, and vice versa. In half-duplex transmission, the entire capacity of a channel is taken over by whichever of the two devices is transmitting at the time. Example, walkie-talkies and CB radios are half-duplex systems. Full-duplex transmission. The full-duplex mode is also called duplex mode. In full-duplex mode, both the stations can transmit and receive information simultaneously. In full-duplex mode, signal going in either direction shares the capacity of the link. This sharing can occur in two ways. Either the link must contain two physically separate parts, one for sending and other for receiving, or the capacity of the channel is divided between signals traveling in opposite directions. Telephone network is the common example of full duplex. When two people are communicating by a telephone line, both can talk and listen at the same time. Protocol transmission. Protocol is a set of rules. The communication lines, modems and other equipment used in the transmission of information between two or more stations are called a data link. Character-oriented protocol. The character-oriented protocol is based on the binary code of a character set. The control characters are used for the purpose of routing data, arranging the text in a desired format, and for the layout of the printed page. The characters that control the transmission are called communication control characters. The SYN character serves as a synchronization agent between the transmitter and receiver, and it has 8-bit code. Input-output devices provides a method for transferring information between internal storage such as memory and CPU registers and external input-output devices. The input-output subsystem of a computer, referred to as I/O, provides an efficient mode of communication between the computer and the outside environment. Input or output devices attached to the computer through I/O ports are called peripherals. Every input-output port has a private address. This is how the computer reads through an input port information from outside, for example, from a keyboard, a mouse, or a temperature sensor. Commonly used input-output devices are monitor, CPU, keyboard, printer, magnetic tape, magnetic disc. Monitor. Video monitors are the most commonly used peripherals. All monitors use cathode ray tube. It contains electron gun, which sends electron to a phosphor-coated screen in front of the tube. The beam is deflected horizontally or vertically with the help of a focusing system. Electron beam is sent to a particular position. Horizontal and vertical signal deflects the beam, causing the electron to hit the screen to produce a visual pattern. CPU, Central Processing Unit. It performs operations at very high speed, and it contains memory unit, control unit, and logic unit. Universal Serial Bus, USB. This is now a very common interface for use with printers, scanners, digital cameras, and it can also be used for keyboards and mice. It allows hot swapping, which means that you can plug and unplug it while the computer is on. You can attach up to 128 USB devices at the same time using hubs in a daisy chain. The USB connection also provides power to the devices. USB 1 transfer speed 12 megabits per second. USB 2 transfer speed 480 megabits per second. Firewire. This is the standard interface for use with digital video camcorders, some storage devices, and the first Apple iPod. It allows hot swapping, and up to 63 Firewire devices can be connected at the same time. It can supply modest power sources to devices. Keyboard. Keyboard controller scans and reports. Key depressions and releases. Supplies key identity as a scan code. Scan code is like a sequence number of the key. Key's scan code depends on its position on the keyboard. No relation to the ASCII value of the key. Interface through an 8-bit parallel I/O port, originally supported by 8255 Programmable Peripheral Interface Chip (PPI). The keyboard sends an appropriate binary coded form to the computer. Types of interface: USB 2, PS2. Mouse: communicate with pulses from LED, increment or decrement counters. Mice have at least one button. Need click and hold. Movement is smooth, slower than processor. Polling: no submarining. Software configuration. Types of interface: USB 2, PS2. Scanner. Scanners are used to convert graphic images into a digital format suitable for processing in a computer. Text can also be input when the scanner is used with optical character recognition software (OCR). Resolution. The resolution of a scanner is measured in dots per inch (dpi). Note that 600 dpi means that every square inch has 600 by 600 dots, which equals 360,000 dots. The bit depth also affects quality, with modern scanners offering 48-bit depth. Type of interface: USB 2 interface, SCSI. Firewire. Printer. It is a hard copy device which is used to take any copy of information with paper. 3 types of printers are available: daisy wheel printer, dot matrix printer, and laser printer. Types of interface: parallel port and USB 2. Parallel port. A parallel port is a type of interface found on computers, personal or otherwise, for connecting peripherals. In computing, a parallel port is a parallel communication physical interface. It is also known as a printer port or centroids port. Today, the parallel port interface is seeing decreasing use because of the rise of USB or Universal Serial Bus and Firewire IEEE 1394 devices, along with network printing using Ethernet. Network card. Peripheral Component Interconnect (PCI) is a 32-bit computer bus that is also available as a 64-bit bus today. The PCI bus is the most commonly used and found bus in computers today. The network card uses the PCI interface to connect to a LAN or WAN. PCI-X is a higher performance bus that is designed to meet the increased I/O demands of technologies such as fiber channel, gigabit Ethernet, and Ultra 3 SCSI. Up to 133 MHz bus speed, 64-bit bandwidth, and 1 GB per second throughput. More efficient bus operation for easier interface. Split transactions allow an indicator device to make only one data request and relinquish the bus, instead of constantly needing to poll the bus for a response. Byte count that enables indicator to specify in advance the specific number of bytes requested, eliminating the inefficiency of speculative perfectness. Backwards compatibility. Conclusion. In this chapter, we have covered the following aspects of computer arithmetic: asynchronous data transfer, handshaking, asynchronous serial transfer, interrupt-initiated input-output, DMA transfer, interfacing peripherals with CPU, introduction, keyboard, mouse, printer, scanner, network card, introduction to pipelining and linear pipelining processor.